Hello, students. Today we discuss Newton's first law of motion. Newton's first law of motion states that an object at rest or moving at constant velocity will continue doing so unless a net force acts on it. So in this case, this one is at rest and is going to be at rest unless a net force acts on it. And for this case, the object is moving at a constant velocity, and things will be like that unless a net force acts on this object. We can state Newton's first law of motion in a different way using a flow chart like this one. The question you should ask is the net force acting on the object is zero? If the net force acting on the object is zero, then you have two options. The object could be at rest, or the object could be moving at constant velocity. So that's what Newton's first law of motion is saying. The net force is zero, yes, then that object is either just sitting or moving at a constant velocity. Now I see that we are actually talking about net force, velocity, net force, velocity. So it might be a good idea to review or to learn something about net force and velocity, what we mean by net force and velocity. So let's focus on the net force and vectors. A vector quantity in physics is a quantity that is fully described by magnitude and direction. So we need the size of that quantity and we need the direction. Once we can describe something with magnitude and direction, then that's a vector quantity. For example, a force will be an example of a vector quantity. A velocity is an example of a vector quantity. So for example, if you want to talk about force, you might want to say maybe 20 pounds downward or 20 newtons to the left, or maybe 60 newtons to the right. So basically you are talking about the size of the force and also the direction of the force. Some of the quantities you have seen from previous classes are very common, like mass, volume, distance. Some of those quantities are actually scalar quantities. Those quantities can fully be described by size only or magnitude only. So scalars are the quantities that you have seen before coming to this class. Most of you, we have worked with numbers. Now, the way we add scalars is actually easy, just arithmetic addition. Mass, if you have 20 grams and 20 grams, you just add them like that. Volume, if you have 5 gallons and 4 gallons, you just add 5 gallons to 4 gallons, you get 9 gallons. So it's easy to add the scalars. Vectors, we need to actually learn somehow some techniques on adding vectors. So this lesson actually will also help you understand how to add vectors. All right, first of all, let's look at how do we represent a vector. A vector is represented by an arrow and the size of the vector. So this is a force. It is pointing to the right. The arrow shows direction and the magnitude is 5 newtons. If I have a larger vector, maybe 10 newtons, it will have a longer arrow still pointing to the right, and then the magnitude, the size is 10 newtons. All right, so I have the size here or magnitude, and the direction is indicated by the arrows. The longer the arrow, the larger the vector. How do we add vectors? When we add vectors, we have to consider different situations. We are going to consider vectors acting in the same direction and also vectors acting in opposite directions. When they act in the same direction, you basically just add the vectors. For example, here, if I choose the right to be positive, then this will be plus 10 newtons. This one will be plus 5 newtons. So I choose right to be positive and left to be negative numbers. So it is always important when you are adding vectors to choose which one is the right and which one is the left. Usually right is given as positive numbers and left negative numbers. So in this case, I'm going to add them up like that because this 10 has a plus sign in front of it. So it's like a positive vector. And this one is also positive vector here, positive. So plus 10 newtons plus 5 newtons gives you plus 15 newtons. The plus here indicates that it is to the right. All right. For this scenario here, second scenario, since the right is positive, we are adding actually 5 newtons here. You want to add it, add that one to the vector that is pointing to the left is going to pick a minus sign because it's pointing to the left. It picks a negative sign here. And therefore, when you actually add these ones, they actually subtract. So it's 5 newtons minus 2 newtons, which is actually plus 3 newtons, meaning that this vector will be pointing to the right because you chose right to be positive. All right, so that's how we add vectors when they are linear vectors. Sometimes you have vectors that are acting at an angle. So for example, situation number 1, the vectors are acting at actually 90 degrees to each other. So what you do, you complete what we call a parallelogram like that. You basically transfer this vector, the longer vector up there, and you transfer the shorter vector like this. So you transfer it all the way like that. So what you are trying to do here, you are trying to complete a parallelogram, and you draw the diagonal from here. You draw the diagonal all the way there. And then once you do that, you can actually say that the resultant, we call it the resultant, it's actually here. That's the resultant or the net vector. So imagine if this was 4 newtons and this was 3 newtons, then this one will be 3 newtons as well, because it's just the one side of the parallelogram or a rectangle. So 3 newtons, 4 newtons, then you are dealing with a problem like this. It means you are dealing with a problem like this one. 3 newtons, 4 newtons, and you are looking for resultant. What is the resultant? So the resultant will be the net vector you're looking for. Resultant. So resultant is the net force you're looking for, or the net vector. So you're going to use Pythagoras theorem. R squared is equal to 3 squared plus 4 squared, and this gives you 9 plus 16, and this gives you R squared will be 20 what? 16 plus 9, 25. 25. Therefore, R will be square root of 25, and that gives you 5 newtons. So that will be the resultant for this problem. Okay. Sometimes you are given vectors at an angle less than 90 degrees. In this case, you just have to measure the lines. You can just measure using maybe a ruler. So you could measure maybe this one. What would be the length of that? But the first thing to do is to complete the parallelogram as usual. So complete the parallelogram all the way there and extend it all the way there. Okay. So basically what you're doing, you are transferring the vectors like that. And then you draw the diagonal. The diagonal going to be drawn like that. That goes over there. So in this case, your resultant will be this one. All right. You may not have, you cannot apply Pythagoras theorem here because these vectors are not at 90 degrees to each other. So what you're having is this vector, that, and you are saying that this is your resultant here. Let me use a straight line. So you are saying that your resultant is this. So at least you have an idea of the resultant, but you cannot apply Pythagoras theorem because there's no 90-degree angle here. What you do, you just actually do a scale diagram. You actually do the measurement on paper, so you can have an idea of how long this line is. All right. So you would want to know what is maybe the length of this line. Let me see. You would want to know how long this is, okay? And then once you measure this, you have to also tell me, you should know what is this angle, which is usually given. This angle will be given to you. Then you can go ahead and measure this line. Then you can at least have an idea of your resultant using the parallelogram rule. So in this class, we are not actually focusing on that. What we need to do is just to complete the parallelogram and indicate how the resultant will be oriented, or how long the resultant will be with respect to the other components, like this one and this one. All right, so that's what we call a parallelogram rule. You would see people talking about, you might want to read about parallelogram rule of vector addition. So the parallelogram rule tells you how to actually add vectors when they are at an angle. All right, so let's talk about equilibrium rule. Let's talk about equilibrium rule. Now, when the net force acting on an object is zero, the object is said to be in mechanical equilibrium. So if you sum up all the forces, vectors, this is a vector. If you sum up all the forces acting on the object, then the object is said to be, it could be at rest, or it could be moving at constant velocity. That object is said to be in mechanical equilibrium. Here's an example. The scaffold here, or the rod, is actually in mechanical equilibrium. So if we look at all the forces acting on this rod or scaffold, the sum of all the forces must be equal to zero. So if I sum up all the forces, and since they are acting in the y direction, I put sub y here, the forces in the y direction, the answer must be 0. Anything acting upward, I'm going to give it a positive sign. Anything acting downward, I'll give it a negative sign. And then I do my addition, the answer must be 0. For the upward forces, I have 700 newtons, and then plus, I don't know this one, so I just put a question mark, plus that. And then for the downward forces, I have minus 400, so I put minus 400 here, newtons. I have also minus 300, so I'm adding minus 300, and then minus 300 again, minus 300. The answer must be 0. So I made sure that this 700 is positive because it's acting upward. The question mark should be positive, of course, and then everything acting downward will be negative. So I have the weight of the crate. The weight of the crate here is 400, is acting on the scaffold. 300 newtons would be the weight of the scaffold itself, is pulling the scaffold itself downward. And I have another crate here is acting on the scaffold, pulling it downward 300. All these forces are acting downward, so they have a negative sign here. They have a negative sign here. And then this one is positive, is acting upward. Now I have to find out what is the question mark here. All right, so this tells me that 700 newtons. And then if I do my mathematics, minus 400, minus 300, minus 400 is actually minus 1,000, minus 1,000 newtons. The answer must be 0. That's according to the rule of equilibrium. Now, if I do this, I can actually say that my question mark is what? So I can actually say my question mark will be, I transfer this one to the right-hand side. It will be positive 1,000 newtons. And then I transfer this one to the right-hand side, it will be minus 700 newtons. So the question mark I'm looking for will be 1,000 minus 700, which is 300 newtons. So that means the scale here will read 300 newtons, already 300 newtons here, so that if you add 700 here, you get 1,000, and the forces acting downward here must also add up to 1,000. In that case, you have your scaffold or your rod in mechanical equilibrium. Okay, now we can also apply the parallelogram rule to ask ourselves which of the sides of the rope here has more tension. So here is a rope. There's a rope here. It is tied to the ceiling here, and is tied to ceiling here, providing some tension in each one of them due to the weight that is right here. So which one, this side or this side, is has more tension or is being pulled greater? So what we do here, we can apply the parallelogram rule by first of all drawing one single line to represent the weight. So we can draw one line to represent the weight of the box here, or I can put it like let me just because this weight is acting on the node here. Let me see. Yeah, I can just represent it as here as a vector acting downward on the node. And since the box is in equilibrium, I can actually draw opposing force. That is should be the net force, same size like the one acting downward. So this has to be the same size as this this vector. They have to be the same size so that it is in mechanical equilibrium. Then I can complete the parallelogram. So I have to draw a line here that is parallel to this one. So I will try my best. This has to be parallel to this line. It has to be parallel to this line. So something like that. Yep. Somewhere there, I see that this line must be parallel to this line. So let me use an arrow, maybe. I'll use an arrow for that. So let me take an arrow. Again, I have to draw it nicely, so it is parallel to this line. And then I will draw another line that be parallel to this line. Trying to draw a parallelogram like that. So these lines form a parallelogram here. So basically what I'm saying is that this vector has two components. The components are this one and this one. So let me emphasize that. I'll use a different color. I'll use a different color, maybe this one. So this line will represent the vector in that direction. So let me see. So these ones are the components of the resultant vector right here. So I have this component and I have this component. I have these components and I know that now this is shorter and this is longer. This is longer. That means there's more tension in this rope than this one. All right. So you first of all draw the vector, and then you draw the resultant, which must be equal to this one because the box is in equilibrium. Since it's in equilibrium, you can draw the same arrows. The one pointing down, another one pointing up must be the same length. Then you complete a parallelogram, making sure that this will be the diagonal of your parallelogram. Then making sure that you have parallel sides. Then you can tell that this side is longer or larger compared to this side. All right, so this side is larger. Okay, so in conclusion, we see that this side is larger. It's larger. So this one is larger. Okay, or greater. So larger tension or greater tension. All right, so let's now finish our discussion by looking at dynamics of, dynamic equilibrium. So it is possible, as we have seen according to Newton's first law of motion, an object can have a net force of 0, but it still be in motion. As long as the forces sum up to 0, the vector sum of the forces sum up to 0, then you are going to see that the object can still be in motion. So what we see here is that the applied force is 70 newtons and the frictional force is 70 newtons. These forces actually balance out. If you were to do the mathematics, sum of the forces in the x direction equal to 0, you are going to see that the right one, you have plus 70 newtons, and plus the one acting to the left is friction, 70 newtons, and the result will be 0. So you have actually achieved the dynamic equilibrium. If something is in motion at a constant velocity, we call that dynamic equilibrium. When something is at rest and the net force is 0, we call that one a static equilibrium. So I want you to review about static versus dynamic equilibrium. Dynamic equilibrium. Okay, so this one is just an example of dynamic equilibrium where something is in motion, but the net force is 0. And the static would be an object just being balanced forces, but just at rest. All right, let's see. We are going to finish by looking at flipping a coin in a high-speed airplane. Newton's first law of motion is telling us that when the net force is 0, the object could either be at rest or moving at a constant velocity. When we say constant velocity, we mean constant speed and constant direction. When we say constant velocity, we mean constant speed and constant direction. So the object is maintaining the same speed and is moving in the same direction. So Newton is telling us that being at rest and moving at a constant velocity are synonymous. They are similar situations. How? Because if we perform experiments in an airplane that is moving very fast, the experiments that we perform are similar to the experiments that you can perform when you are in your house at rest. Or when maybe the airplane is at rest, is just sitting on the at the airport, the experiments you can do are the same. So if you flip a coin, in a high-speed airplane, we see that the coin behaves as if the airplane were at rest, and the coin keeps up with the flipper. So it keeps up with the flipper. You don't even realize that the plane is moving. That is actually one of the important things about Newton's first law of motion, that being at rest and moving at a constant velocity are actually similar situations. Now, so as you can see, gravity affects only the vertical motion of the coin. And therefore, due to inertia, we see that although the airplane is moving fast, as long as it's constant velocity, the behavior is just like being at rest. So that's a very interesting idea or conclusion that we can get from Newton's first law of motion. Again, being at rest and moving at a constant velocity are very similar situations. Our observations in a fast-moving airplane, as long as it's constant velocity, are very similar to the observations we have when we are at rest in our house, in a classroom, or in a stationary airplane. Our experiments actually gives us the same results. Interesting. All right, I'll stop here. Let me know if you have any questions. I'll be happy to answer your questions. Thank you.